Hi, I'm Res Paisha and this video is about climate science. Recently I had a bit of a chinwag with some people about the climate system and science in general. One person said that the hole in the ozone layer was bunk, and so too was quantum mechanics, relativity and global warming. But then he made an exception for gravity. He said that gravity was proven. I then asked him which of the many theories of gravity that he thought was proven. He replied, none of them. Gravity is simply that objects fall. That's proven. So it got me thinking. What seemed to be required is simple, easy to understand examples of the physical principles involved. With another person I had a conversation about global warming being a question of planetary energy balance, to which she replied that energy does not need to be dissipated because energy is consumed. It gets used up. So this video is about the fundamentals of the science, but illustrated where possible with common everyday examples. So we'll have a look at a pendulum, the colours of the rainbow, a hot piece of iron, before we get on to looking at a few simple climate models. First definition, energy. Energy is the ability to do work. The main unit for energy is the joule. Consider this scenario. We have a man pushing a car. At first the handbrake is on, and even though the man tries hard, he can't budge the car. The force applied by the man is being opposed by the frictional shear force between the tyres and the road. No work is being done. When the car's handbrake is released, the man finds that he can move the car. Work is now being done to the car. However, the man always had the energy or ability to move the car. Releasing the handbrake did not create the energy. This leads us to the conservation of energy. Energy may either be created or destroyed. Here I have a pendulum. It's a good example of how energy is conserved. At the top of its swing it has no velocity but has potential energy. At the bottom of its swing it has kinetic energy equal to the potential energy lost. Halfway down its swing it has lost half its potential energy and gained half its maximum kinetic energy. The sum total of the energy in an isolated system is always constant. There are four fundamental modes of heat transfer. Conduction, the transfer of energy between objects that are in physical contact. Convection, the transfer of energy between an object and its environment due to fluid motion. Radiation, the transfer of energy to or from a body by means of the emission or absorption of electromagnetic radiation. And the fourth, evection, the transfer of energy from one location to another as a side effect of the physically moving an object containing that energy. Here on the left we have a common item, a vacuum flask. Perhaps you've taken one on a picnic to keep your tea or coffee warm. On the right is a cross-section of the flask. Inside it has two shells with the air pumped out between them. This prevents heat loss by conduction and convection, leaving radiation as the only means by which it can lose heat. However, the outer side of the inner vessel and the inner side of the outer vessel are silvered to reduce the loss or gain of heat by radiation. The Earth sits in a vacuum of space. Radiation is therefore the only way the Earth can gain or lose energy. Walking up a hill is an example of doing work. However, I could run up a hill quickly or walk up slowly. The same amount of work is done, but these two examples are very different. Power is the time rate of doing work. The main unit for power is the watt. It equates to 1 joule of energy being produced in a single second. If I produce power at the rate of 1 watt for a period of 10 seconds, I've produced 10 joules. Now let's look at a hydroelectric power generator. Water is fed into a turbine from a header pipe. The turbine converts the energy of the flowing water into rotational mechanical energy. Then the mechanical energy is converted into electrical energy in the generator above. At the Tumut 3 hydroelectric power station, each generator is rated at being able to produce 250 megawatts that is 250 million watts. Furthermore, because of the large numbers involved, power generation companies tend to speak of energy produced in terms of megawatt hours, a single watt hour being 3,600 joules, because there are 3,600 seconds in an hour. If I run a single generator at T3 at its rated power for 1 hour, I produce 250 megawatt hours of energy. On the left, we're using a triangular glass prism to split white light into its component colours. The shorter the wavelength, the more light is refracted. What we end up with is the frequency spectrum of light. But, moreover, the electromagnetic spectrum is not just composed of light that we can see. Beyond violet is ultraviolet, and above red is infrared. Herschel was an astronomer of some note. Having found Uranus in 1781, he pondered the relationship between the various colours of light and temperature. He used a prism to split sunlight into its constituent colours. He placed a thermometer with a blackened bulb in the path of the light for each colour to measure its temperature. He then placed the thermometer just beyond red and got a surprise. He found that this invisible colour was the hottest. He called this colour calorific rays, after the Latin word for heat. We now call it infrared. Here we have a picture of the human eye. You'll notice that the pupil appears black, yet in reality it's a hole. The perfect black body is one that absorbs all incident light, just like as if it was a hole. We can see here a number of eye bolts. One is glowing reddish yellow. From experience, I'm sure that we've all know it's hot. In fact, we use the term red hot. What we are seeing is known as blackbody radiation. The eye of the bolt is yellow, then moving down the shaft it's red, and further down the shaft it's not visibly glowing. And I say not visibly glowing because it is glowing but not in the visible spectrum. Our eyes just can't detect infrared light. However, you may well have seen night vision photography of a person's body heat. You see, cameras can detect infrared. Focusing once again on this screen image, the eye of the bolt that appears yellow is hotter than the shaft that appears red. The red part of the shaft near its eye is hotter than the infrared section of the shaft lower down. This leads us to Planck's law. In the same way that a hole is a good model for the absorption of radiation by a black body, Max Planck modelled the radiation of a body as the radiation exiting from a hole in one wall of an oven. On the screen is the formula for the intensity of light emitted by a black body, which is both a function of its absolute temperature, denoted by capital T, and the wavelength, lambda, of the light emitted. In this equation, the other symbols are constants. H is Planck's constant, c is the speed of light, and k is Boltzmann's constant. Planck's law yields a series of blackbody radiation curves. Each curve represents the black body at a different temperature. The red curve, marked T equals 5500 K, is for an object that has a temperature of 5500 degrees Kelvin. The horizontal axis, marked lambda, is the wavelength of the emitted light. Each curve looks like an elongated bell. For the red curve, the maximum point on the bell corresponds to a wavelength a little over 500 nanometers. For the green curve, just under 600, 650 for the blue, 700 for the blue-green, and 800 for the black curve. This takes us to Wien's law. The wavelength of energy emitted from a body increases with decreasing temperature. Lambda max represents the wavelength that corresponds to the maximum blackbody energy output for each temperature curve. Lambda max is inversely proportional to the temperature of the body. Lambda max equals B divided by T, the absolute temperature, and is represented by the black curve on the graph. When we talk about the surface temperature of a star, we talk about its blackbody equivalent temperature. Nobody can go to the sun and measure its temperature with a thermometer. It's far too hot. In fact, our sun has a blackbody radiation curve similar to the red plot on the previous graph. So we talk about it as having a blackbody equivalent temperature of close to 5,500 degrees K. It's actually 5,777 degrees Kelvin. Here we have a comparison between the sun's actual output and its theoretical blackbody spectrum. They are fairly close. Treating the sun as a perfect black body makes a good approximation. Stefan-Boltzmann's law. A body in space radiates an amount of energy proportional to the fourth power of its temperature. The warmer the body, the more energy is lost. Power per unit area, that's the P over A, equals sigma, a constant, multiplied by temperature in Kelvin raised to the fourth power. Blackbody radiation emitted by the sun. Applying Stefan-Boltzmann's law at the surface of the sun, we get that the radiation emitted is 63.16 megawatts per square metre. The inverse square law. The intensity from a point source falls off with the square of the distance. Just by looking at this diagram, you should be able to see the logic of this law. Now, the sun is not actually a point source, it's a ball of radius r. However, we know that the blackbody radiation emitted from a unit area on the surface of the sun, and we know that the Earth is approximately 215 sun radiuses away from the centre of the sun. The sun's irradiance reaching the Earth. Now, the sun is not really a point source, but what we know is that the blackbody radiation leaving a unit of area of the surface of the sun at a distance of 1 sun radius from its centre. Now, here's the trick. We're going to treat the sun as though it was a point source, with the value of the blackbody radiation at its surface as though it was passing through the surface on its way to the Earth. Now we can apply the inverse square law to the problem. The Earth is a distance of approximately 215 sun radiuses away from the centre of the sun. Blackbody radiation emitted by the sun, as we calculated before, was 63 megawatts per metre squared. And attenuating this by the square of the distance, 215 squared, gives 1,366 watts per square metre reaching the Earth. The Earth intercepts the same amount of radiation from the sun as that of a disk with the same diameter as the Earth. Conceptually, we could think of the Earth as though it was chopped in half. Radiation from the sun before it enters the atmosphere equals the irradiance, 1,366 watts per metre squared, multiplied by the area of the disk, r being the radius of the Earth, 6,378 kilometres. Crunching the numbers, we get 174 petawatts. A petawatt being 10 raised to the power of 15 watts. If the moon was a perfect black body, we wouldn't be able to see it. A percentage of the light that strikes the moon is reflected and not absorbed. Albedo is the Latin word meaning whiteness. In astronomy and climate science, albedo is defined as the ratio of reflected radiation from the surface to incident radiation upon it. We can measure light directly from the moon and compare it to light from the sun. Ostensibly, the light that strikes the Earth is the same intensity as the light that reaches the moon. According to Wikipedia, the full moon is about 500,000 times fainter than the sun. The moon's mean orbital distance is 384,000 kilometres away, and its mean radius is 1.7 thousand kilometres, which means that we are about 221 moon radii away. If the moon acted like a mirror, the moon would appear 49,000 times fainter than the sun, that is, 221 squared. So the albedo is about 49,000 divided by 500,000, or just under 10%. The Moon's actual albedo is 0.11 according to the NASA facts sheet, meaning only 11% of sunlight incident on the Moon is reflected. You can't see it here in this photo, but if you were to look at it physically, it's possible to see the dark side of the Moon. That is because of the Earth's albedo. The Earth reflects sunlight onto the dark side of the Moon. The light reflected back from the Moon from its dark side is therefore the result of the Earth's albedo in combination with the Moon's albedo. But since we can calculate the Moon's albedo independently from the Earth's, we can isolate the Earth's albedo from the combination. So even before the space age and satellites, scientists were able to measure the albedo effect of the Earth. Of course, it can be done much more directly now using satellites and, of course, much more accurately. The Earth is comprised of approximately 70% oceans and 30% land. The land is further divided into deserts and forests, each with their own albedo effect, and at the poles, ice caps. The Earth's overall albedo of 0.30 is an average. Deforestation and man's farming practices can affect the Earth's albedo. Global warming by melting the ice caps and glaciers can also affect the albedo. Pictorially, we have 174 petawatts coming from the Sun and intercepted by the Earth. 30% or 52 petawatts is reflected by the Earth's albedo. The remaining 122 petawatts is absorbed by the Earth, and this heats the Earth. The 30% that was reflected does not heat the Earth in any way at all. Whether it's global warming or cooling is a question of balance. If the Earth gains net energy, it warms up. If it loses net energy, it cools down. And if it is in equilibrium, it is neither cooling nor warming. Equilibrium from a global energy perspective does not mean that we won't see changes in the weather from one year to the next. We will. The weather system is quite capable of shuffling the energy around internally, as in the case of La Nina and El Nino events. Let's consider the situation where the Earth doesn't have an atmosphere. For equilibrium, incoming power must equal outgoing power. Because space is a vacuum, the only way the Earth can lose heat energy is by way of radiation. In the equation, S is the sun's irradiance at the top of the troposphere. We previously calculated this to be 1366 watts per square metre. It can also be measured directly by satellite. Pi r squared is the area of the sun's radiation intercepted by the Earth, where r is the Earth's radius. 1 minus alpha is the radiation absorbed by the Earth, where alpha is the Earth's albedo. Before looking at the right-hand side of the equation, we'll look at a couple of definitions. A grey body is a body that emits radiation in constant proportion to the corresponding blackbody radiation. Power per unit area equals epsilon sigma T raised to the power of 4, where epsilon is the constant of emissivity, and sigma T to the power of 4 is the Stefan-Boltzmann blackbody radiation. Emissivity, epsilon, is the ability of a surface to emit energy by radiation relative to that of a black body. A black body is the same as a grey body, having an emissivity of 1. Emissivity is a ratio and has no units. Now, returning to our incoming power equals outgoing power equation and looking at the right hand side, 4 pi r squared is the surface area of the Earth, a sphere of radius r. Epsilon sigma T raised to the power of 4 is the formula for grey body radiation of the Earth. In this model, we are making the simplification that the surface of the Earth has a constant temperature over its whole surface. However, what we're looking for from this model is the average equivalent temperature of the Earth. We have already calculated the incoming power. The Sun's radiance less the albedo effect to be 122 petawatts. On the right-hand side of the equation, R equals 6,378 kilometres, epsilon equals 0.98, and sigma equals 5.67 by 10 to the minus 8. This equation can be solved for T, and after crunching the numbers, we find T to be negative 16 degrees centigrade. The global mean temperature is about 15 degrees centigrade. That is 31 degrees higher than our calculated temperature for the Earth had it not have had an atmosphere. Let's investigate how much we need to increase the incoming power to produce a global mean temperature of 15 degrees centigrade, 15 degrees being 288 degrees Kelvin. So we use the same formula as before. Power incoming equals 4 pi r squared epsilon sigma T raised to the power of 4. Then substituting the values into the formula, we obtain Pi equals 195 petawatts. That is 60% more than the Sun is currently providing. Even if the albedo was set to 0, we'd only get to 174 petawatts of absorption, still well short of the 195 petawatts required. As a thought experiment, I've modelled the feedback required to produce a 60% increase in input to the Earth. Note that the 60% increase is achieved with a feedback of only 37.5%. Also note that there are two systems in equilibrium here. The Earth itself with an input and output of 195 petawatts, and then the overall Earth with its feedback system having an input of 122 petawatts from the Sun and a radiated output of the same. Here we have the same feedback model, but expressed in terms of watts per metre squared, instead of the previous values quoted for the Earth as a whole. The input from the Sun is 240 watts per metre squared. Next, Kirchhoff's law. Objects that absorb radiation strongly at a given wavelength will emit strongly at the same wavelength, whilst conceptually emissivity is different to absorptivity. Their value is the same according to Mr. Kirchhoff for any given wavelength. You'll often see alpha for absorptivity used interchangeably with epsilon for emissivity in equations. I'm going to look at a model with a single layer of greenhouse gas. In our model, the yellow ball and red arrow represents the radiation from the Sun after reflected radiation has been removed, that is, the albedo effect. From our last feedback slide, S was calculated to be 240 watts per metre squared. The green bar at the bottom represents the Earth's surface. It has a temperature, TE, of 288 degrees Kelvin, or 15 degrees centigrade. Radiation from the Earth is shown by the green arrows. The horizontal grey bar represents the greenhouse gases in the atmosphere. They have a temperature TA. Radiation from the greenhouse gas layer is shown by the grey arrows. G is the Stefan-Boltzmann blackbody radiation of the Earth. That is, sigma TE raised to the power of 4. And A is the blackbody radiation for each of the two hemispheres of radiation of the greenhouse gas layer. That is, sigma TA raised to the power of 4. Whilst a solid body only radiates in one hemisphere, a thin layer can radiate in two, one up and one down. The emissivity of the air and the Earth is represented by epsilon A and epsilon E, respectively, and because of Kirchhoff's law represents the absorptivity values also. Firstly, the Sun's radiation S is absorbed by the Earth. Then following the green line, the Earth radiates energy as a grey body. That is epsilon E times its blackbody radiation. The greenhouse layer then absorbs part of this radiation, given by epsilon A, epsilon E, G. The radiation not absorbed passes straight through and off into space. That's the term 1 minus epsilon A times epsilon E, G. Next, the greenhouse gas layer emits grey-body radiation. Now, following the grey lines, that is epsilon A times its blackbody radiation. You'll note that the upward-going hemisphere of radiation from the greenhouse layer is emitted off into space. The downward hemisphere of radiation from the greenhouse gas layer mostly goes into heating the Earth. That is epsilon E, epsilon A times the blackbody radiation A. A small amount is not absorbed but reflected upwards. For equilibrium, the energy into the greenhouse gas layer must equal the energy out. That is, by definition. This energy balance equation is shown in the blue box. In the lower highlighted box is the energy balance equation for the Earth's surface. We're going to use our greenhouse gas model to calculate the emissivity of the greenhouse gas layer required to produce a surface temperature of 288 degrees Kelvin. The first line is the atmospheric greenhouse gas layer's energy balance equation from the previous diagram. The second is the Earth's surface energy balance equation, also from the previous diagram. The third is the Blackbody Stefan-Boltzmann formula for the ground, and the fourth is the Blackbody Stefan-Boltzmann formula for the greenhouse gas layer. Then we can solve from the simultaneous equations to obtain an expression for epsilon A. Then substituting the Earth's emissivity of 0.98, the Stefan-Boltzmann constant of 5.67 by 10 to the minus 8, and a surface temperature of the Earth as 288 degrees Kelvin, we obtain a value for the emissivity of the atmosphere of 75.4%. Next, we can calculate the temperature of our greenhouse gas layer. You can pause the video if you want to look at the derivation. Here we find the temperature, TA, to be 241 degrees Kelvin. Here we have our previous greenhouse gas model updated with the new information. Interestingly, the simple feedback model produced results within 1 watt per square metre of those obtained in this model. However, this model gives additional information. We found the emissivity and temperature of the greenhouse gas layer, that is 0.754 and 241 degrees Kelvin, respectively. Given that the lapse rate, that's the atmospheric fall in temperature with height, varies from about 5 to 10 degrees centigrade per kilometre, our hypothetical greenhouse gas layer would be between 5 and 10 kilometres off the ground, a location that is in the upper half of the troposphere. From a modelling point of view, not an unreasonable result. The top graph shows our modelled absorptivity. The lower graph shows the atmosphere's actual absorptivity. The central blue bar between the two graphs marks the incoming radiation spectrum from the Sun, and the red bar the outgoing infrared. In our model, the albedo effect was the result of measurement. As a result, the albedo measurement already accounts for the actual spectral effect in our model for incoming radiation. However, we modelled the outgoing emissivity as a flat 75.4%. So from our model, 24.6% of upgoing thermal infrared radiation was transmitted. The measure of accuracy of our model is a question of how closely the two graphs match transmission-wise, especially in the infrared region. It has been noted that the actual upgoing thermal infrared radiation transmitted varies from 15 to 30%, depending on the atmospheric water vapour content. Our calculated value is near the middle of the actual range. Due to this similarity, we can conclude that the greenhouse effect is sufficient to account for the additional 31 degrees centigrade of temperature over and above the temperature of the Earth had it not have had an atmosphere. On the screen we have two coincident measurements of the infrared emission spectrum. The top diagram shows the measurement taken from 20 kilometres above the Arctic looking down, and the other is from the ground below looking up. One resembles the negative image of the other. Together these two graphs represent the smoking gun, pointing to the atmosphere being responsible for turning around the outgoing infrared blackbody radiation of the Earth and sending it back to the Earth. The dotted lines on both graphs represent various Planck blackbody radiation temperature curves. Now we have found the smoking gun. What about the bullet? Yes, we have that too. It's the lower graph. It is a snapshot of the extra heat radiation just as it reaches the Earth. It is the evidence of the atmospheric feedback of the greenhouse effect. It is this radiation that provides the additional 60% of heating to the Earth's surface. Here we find our causation. Summary. We've looked at Planck's, Wien's and Stefan-Boltzmann's laws. But really deep down you should have realised that in one sense you already knew these laws. You already knew that light is comprised of different colours, each colour being a different frequency range of light. Anyone with an electric bar radiator knows that objects radiate. Most people already know that as an object gets hotter and hotter, its colour changes, and change is consistent with the sequence of the colours of the rainbow. Don't forget about the pendulum principle, that is, the conservation of energy. If the Earth receives energy from space, to remain in equilibrium it must emit the same amount of energy back into space. Based on solid scientific laws, we know that if the Earth did not have an atmosphere, it would be colder, indeed very much colder. However, the Earth with its atmosphere is not frozen but is approximately 31 degrees centigrade warmer. We calculated that the Sun would have to be 60% more radiant to achieve the same result. However, the Sun's output was a measured result, so we don't have the liberty of turning it up or varying it in any way. We do know one thing though. Energy must be going into the Earth, otherwise we would not be able to get the additional 31 degrees. Furthermore, we know that this elevated temperature causes more energy to go out. We found that a feedback of 37.5% would be sufficient to produce the increase of 31 degrees. Melting ice is a feedback that lowers the albedo, but here again the albedo was a measured attribute that we don't have the option of changing. Furthermore, if we zeroed the albedo effect altogether, it would not be sufficient to account for the full 31 degrees. We had a look at modelling the greenhouse gas effect. We found that it was capable of explaining the additional temperature. The model managed this whilst maintaining the amount of energy emitted back into space, that is, equilibrium. We also have correlation, as the atmosphere certainly contains greenhouse gases. Our model made a prediction. The prediction was that the upgoing thermal radiation transmitted would be about 25.5%, and that is in the correct range. The atmospheric greenhouse gas temperature was also in the correct range. Furthermore, it is possible to directly measure the downgoing infrared radiation. We know it is there. That is the sort of proof we have of the concept. However, we have dealt only with equilibrium here and not the enhanced greenhouse effect. But that'll have to wait for another video.